From the distant sky comes a wave of change and motion. The air and earth adopt an expectant tone. The earth and all living things await rain.
Clouds, huge reservoirs of airborne water. In the beginning, most of the Earth's water was stored in clouds, forming a dense white envelope around the planet. Gradually, as the Earth cooled, the first rains began to fall, continuing without pause for thousands of centuries, filling the ocean basins. Now the oceans hold most of the Earth's water. From the ocean's surface, water evaporates continually, returning to the atmosphere, sometimes forming clouds. Time-lapse photography enables us to observe the development of clouds in detail. The sun's energy heats the Earth. When air near the surface is warmed, it rises, carrying water vapor upward. As warm air rises, it cools, and the water vapor in the air condenses into water droplets. Here, moisture in the air is condensing on the surface of a cold pitcher. Ice in the pitcher is cooling the surrounding air. But how is the atmosphere cooled so that clouds may form? One important factor is a change in air pressure. The air pressure inside this chamber is greater than the pressure outside the chamber. We'll observe the temperature of the air in the chamber as the pressure is decreased. When air is released from the chamber, the pressure in the chamber decreases and the temperature drops. In the same way, all gases cool as they expand. Because air pressure decreases with height, rising air expands and cools. And this cooling causes water vapor to condense, forming clouds. We can form a cloud in the laboratory by simulating atmospheric conditions. This sealed chamber contains a small quantity of water. We'll decrease air pressure in the chamber by lifting this plunger. This causes the air and water vapor in the chamber to expand and cool. In subdued light, we can see a cloud form. A laser beam will help us evaluate the density of the cloud. The beam is faint, indicating that the cloud is not very dense. We'll introduce a small quantity of soluble salt into the chamber. Now the laser beam reveals a much denser cloud. The number of cloud droplets in the chamber is increased by the addition of the salt particles. These particles are called condensation nuclei. They provide microscopic surfaces upon which water vapor condenses. Under a microscope, we can see water vapor condensing on nuclei. Particles of salt are absorbing water vapor from the surrounding air. In the atmosphere, ocean salts, smoke, dust, and other minute particles act as condensation nuclei. These condensation nuclei help to produce clouds and rainfall. A single cloud contains billions of microscopic droplets, storing tons of water. But cloud droplets are too small to fall as rain. Raindrops are much larger than cloud droplets. It is difficult to measure raindrops as they fall to Earth, but this device will help us estimate their size. As raindrops fall through the screen, they leave a shadow behind. In the laboratory, the raindrop pattern on the screen is measured. These raindrops are approximately 5 millimeters in diameter. Cloud droplets are more difficult to measure. To study cloud droplets, meteorologists use real clouds as a laboratory. As the aircraft travels through a cloud, a specially treated film is exposed to cloud droplets. The film is then studied and analyzed. Under polarized light, a cloud track on the film becomes visible. Highly magnified, this track reveals thousands of impressions made by cloud droplets. The larger particles are ice nuclei. The average size of these droplets is 10 micrometers, or 1/100th of a millimeter. It would take more than 1 million droplets of this size to form one raindrop. How then do cloud droplets become raindrops? To form raindrops, millions of cloud droplets must come together and coalesce. In this airflow chamber, we'll observe cloud droplets in an updraft of warm air. These droplets are not interacting to form larger drops. In this airflow chamber, we see small droplets rising, while at the same time, larger droplets are descending. How do droplets come together so that coalescence can occur? In a cloud, not all droplets are the same size. As large droplets fall, they may overtake small droplets and combine with them, or coalesce, forming larger drops as they descend. Some meteorologists believe that coalescence is influenced by electrical charges in the atmosphere, an idea originated by Benjamin Franklin. These two streams of water will help us observe the effect of electrical charges on coalescence. By means of high-speed photography, we see that the streams consist of individual drops that collide, but do not coalesce. Now the two streams are passing through an electrostatic field. The drops coalesce, forming larger drops. In a similar way, it is likely that electrical charges, such as those in a thundercloud, may induce the formation of raindrops. But there is another way raindrops may form. In some clouds, temperatures are below the freezing point of water. Under these conditions, cloud droplets, although they are very cold, do not necessarily freeze. They remain in a supercooled liquid state. The temperature of this water is minus 10 degrees Celsius. Even at this low temperature, the drops remain supercooled. On contact with a foreign substance, the drops freeze, as we see by polarized light. This shows that in addition to low temperature, nuclei, such as particles of dust or other solids, are needed for ice crystals to form. These microscopic particles, called ice nuclei, are a key to the formation of raindrops in supercooled clouds. Time-lapse photography reveals the growth of ice crystals as water vapor is deposited directly on the ice surface. We can also observe the growth of ice crystals using an ordinary freezer. Breathing into the freezer produces a visible cloud. In the same way, our breath becomes visible on a cold day. We have created a miniature cloud of supercooled droplets in the freezer. Now we'll introduce some nuclei, a few shavings of dry ice, frozen carbon dioxide. Immediately, ice crystals begin to form. The particles of dry ice serve as nuclei, converting cloud droplets into minute ice crystals. The heavier ice crystals begin to fall. In clouds, ice crystals may grow large enough to fall. Those that fall into warm air melt and become rain. Much of the Earth's rainfall forms in this way. But falling ice crystals can initiate other forms of precipitation. Thunderstorms are often accompanied by hail, accumulations of ice that sometimes descend with devastating force. Hail is the most destructive form of precipitation. The damage caused by hail amounts to billions of dollars each year. After a storm, meteorologists collect hailstones to investigate their internal structure. A hailstone that began as a tiny ice crystal may grow to a diameter of more than 15 centimeters and weigh over half a kilogram. A thin section is cut from the center of a hailstone. Under polarized light, a circular pattern is revealed. strong evidence that hail forms in layers. This offers a clue to the process of hail formation in clouds. As an ice particle descends through a supercooled cloud, it accumulates a layer of frozen droplets. Powerful storm currents may carry the crystal upward through colder air, freezing additional water around it. The repetition of this process, upward and downward through the cloud, enlarges the hailstone layer by layer. When hailstones become too large to remain suspended in the cloud, they plummet to earth. Thunderstorms that result in hail usually occur in spring and summer. In colder weather, raindrops falling through cold air form ice pellets, commonly called sleet. Sometimes supercooled raindrops freeze on impact, coating objects with ice and adding perilous weight to trees and shrubbery. Snowflakes are ice crystals that fall to earth without melting. Under controlled conditions, the growth of snow crystals can be observed. A microscopic particle serves as a nucleus. As water vapor is deposited, the delicate configuration of a snowflake develops. Although it is a valuable form of precipitation, there are times when we may not appreciate the beauty and benefits of snow. Our increased understanding of how raindrops form is enabling meteorologists to influence the weather. One important discovery is the ability to increase rain or snowfall through cloud seeding. In cloud seeding, substances such as dry ice or silver iodide scattered into a cloud act as ice nuclei. But we must still depend on the right conditions in the atmosphere to stimulate precipitation. Another way we are influencing rainfall is through air pollution. Some urban and industrial pollutants create an overabundance of nuclei in the atmosphere, affecting cloud formations and changing normal rain patterns. Over prolonged periods, changes in rainfall can have a detrimental effect on life in a region. 7 centuries ago, the inhabitants of these cities in the American Southwest were forced to abandon this region because of drought. In the 1970s, diminished rainfall in regions of Africa and Asia has also resulted in widespread drought and desolation. Without water, there is famine and death. In the future, how will changing rain patterns affect life on Earth? Will we be able to modify rainfall to meet our needs as we increase our understanding of what makes rain?